Welcome to section 2.3. This is a long section in terms of content, but it is not a difficult section. Just a lot of little details. Let's get started. First thing you need to know is what is average rate of change of a function. Average rate of change, also known as AROC, of a function is the change in the value of the dependent variable divided by the change in the value of the independent variable. This is just another way of saying y, and this is just another way of saying x. Okay, in other words, your AROC, your average rate of change, is given by the formula y2 minus y1 over x2 minus x1. Okay, now in pre-calculus, we start to use the function notation quite a bit because it's heavily used in calculus. In other words, instead of using y2 and y1, we know that y2 comes from plugging x2 into the function f, right? And we know that y1 is the result of plugging x1 into the function f. So we typically go with this notation now. It's a little more mature, and it also shows us the connection between denominator and numerator. Okay, so we're going to use this formula for AROC throughout the year. Okay, let's try to find the average rate of change for this very simple function, y equals 5x, or f of x equals 5x. Okay, since we're going from x equals 1 to x equals 6, we simply would just do AROC equals, and this would be like our x1 and our x2. So we're going to basically be doing f of 6 minus f of 1 over 6 minus 1. The denominator is obviously 5, but the numerator should be calculated. So the function is the 5 times a number function. That's the rule. You multiply the number by 5. So in this case, we would be finding f of 6, which is 5 times 6, and f of 1, which is 5 times 1. And we basically end up getting 30 minus 5, which is 25, all over 5, which in turn is 5. So all of this just turned out to be 5 on this problem. Okay, 5. Now let's talk about real briefly what it means. So sometimes I like to wait till an example is done to help you understand. So this problem is kind of trivial. That just means real simplistic. This is the line y equals 5x. If you go over 1, it goes up 5. If you go over 2, it goes up 10, and so on. It's just a line. It actually starts at the origin. So we just finished our unit on linear functions when we did 2.2. So this is the function f of x. What we just did is we went basically from x equals 1 to x equals 6. So you can see, if I kind of zoom out, this is the point 1, 5. And if you go out to 2, 3, 4, 5, 6, it actually would end up being all the way up at 30. So if that's 1, 5, this might be 10, 15, 20, 25, 30. So we basically went from this red point, 1, 5, to this red point, 630. And we found the slope of this line, is what we did, okay? And you might say, that's kind of funny, because that is the actual function. You're right, f of x is right here. It's right up against this segment we just drew. So we just found the, I guess you could say, we just found the slope of this line that goes through 1, 5, and 630, but at the same time, we were also finding the slope of the red graph. So it's kind of silly because we found the slope of the blue when we could have just found the slope of the red. Kind of a silly example. Let's look at the next one, though. It's more meaningful. In this example, we're trying to find the average rate of change of f of x equals 2 over x plus 1 from x equals 1 to x equals 6. So same instructions, different function entirely. If we just take the formula blindly, we're supposed to do f of 6 minus f of 1 again, all over 6 minus 1. This time it's 2 over 6 plus 1 minus 2 over 1 plus 1 all over 6 minus 1. So the bottom's still 5, but the top is calculated using the 2 over something plus 1 rule. So the 6 and the 1 I got from my inputs here. Okay, so this is 2 over 7 minus 2 over 2 all over 5. So what we probably should do on something like this, if you remember from your Algebra 2 class, is maybe simplify it as much as possible and then clear the complex fraction. Maybe we can multiply top and bottom by 7. That might be a good strategy. So this would basically give me 2 minus 7 all over 35, so that the answer is negative 5 over 35, or simplifying that, negative 1 over 7. So what exactly is this thing? This is the average rate of change. I'm going to argue that it's actually the slope of a secant line. So what is the slope of a secant line? Well, the curve y equals 2 over x plus 1 is a little more complicated than last time. So you might not remember how to graph these. It's not really my focus right now, so I don't want to stress about it too much. But the graph basically looks like this red thing, okay? This is the graph. It looks something like this. And what we just did is we basically connected from x equals 1 to x equals 6. So this point here, it's not a very good drawing. Yeah, it's basically this point here to this point over here. And it should look like my red curve is above the x-axis. So maybe I should go back a little bit with my sketching. This graph doesn't quite touch the x-axis. So it goes more like that. So anyway, without getting too detailed, we're going from this point to this point, and we're calculating the slope. So notice that this line here, this green line, it doesn't really hug the curve that well. It touches 2 points on the curve, but it doesn't really hug the curve the same way this last example did. Remember this last example, the blue line here, I'll color it green, it's actually hugging the red graph entirely. But this is a curve, so you're never going to make a line hug a curve perfectly. But we are passing through the points 1, f of 1, and 6, f of 6. And we basically, when we calculated a rock, we were calculating the slope of that green line. Okay? Okay, we could keep getting carried away and keep trying new things, but basically I want to say what's going on is a rock is the calculation of the slope of a secant line. So it calculates slopes of secant lines. It calculates, Mr. Short wrote that wrong, calculates slopes of secant lines. You might say, what is a secant line? You learned that in geometry. A secant line is a line that cuts through a curve. Okay. Okay. Next is example 3. Example 3, you can see it's a little more complicated, but it's the same principle. Find a rock. So we're going to go ahead and bust out the formula blindly. So the formula is we're going to be going from 2 to x. So instead of going from 1 to 6, we're going from 2 to x. So this is kind of like your x1. This is kind of like your x2. Remember, the rule was f of x2 minus f of x1 over x2 minus x1. So we're going to be writing f of x minus f of 2 over x minus 2. Notice we did not get 2 numerical inputs. We only got one number, 2, and one letter, x. So we're going to have to play along as best we can. F of x, remember, was the square root of x plus 2. F of 2 is the square root of 2 plus 2. And the bottom is just x minus 2. Excuse me. Rewrite that. Okay, so some of this simplifies a little. Actually, things simplify quite a bit once we get the hang of these. I'm going to go ahead and show you that later, I think. For now, we're just going to take this at face value and calculate it and just leave it unsimplified. Okay, so we're ending up with basically square root of x plus 2 minus square root of 4 all over x minus 2. So this is the answer. Notice that this time it's an expression answer, not a numerical answer. That's because they never told us what x was. But this is almost more valuable in a way because now I can choose any x I want. See, I could choose any x I want. So if I want x to be 10, I could plug in 10 for x, and it will calculate the slope for me. So this graph, just so you know, you don't have to really know this for this problem, but this graph is what we call a radical function, and it's shifted left 2 spaces. We'll review that when we get to 2.4. But it looks something like this, and there is a point over here at x equals 2, of course, and it's right there, and this is the point 2, f of 2, okay? And then we're going to go from here to any other point we want. So say this purple one, or this purple one, or this purple one. And as we choose different x's, the formula that we wrote here, this formula that we just created, its job is to calculate the slope of a line. So let me explain. If you look closely here, you can see that you could connect from 2f of 2 to the first point, or you could connect from 2f of 2 to the second point, or you could connect from 2f of 2 to the third point. See, there's multiple options. So each one is going to have its own slope. And this formula that we just created in yellow will calculate the slope of that line. So this is good for calculating slopes from 2 to somewhere for various secant lines. Okay, all right, let's go to part B. It says now to use the average rate of change found in part A to find the average rate of change from 2 to 3. So the formula that we created was square root of x plus 2 minus 2 all over x minus 2. And this will calculate the slope from 2 to anything. From 2 to anything. We're planning to go from x equals 2 to x equals 3. So we're going to use 3 for our x is the idea. Okay, so if we're going to go from, that says from 2 to x, we're going to use this formula. If we're going to use from 2 to 3, we're going to plug in 3. So we're going to go like this. Instead of square root of x plus 2 minus 2 all over x minus 2, we're going to plug in 3 for that. And this is going to now finally be numerical, of course. So we end up with a rad 5 minus 2 all over 1. In other words, root 5 minus 2, which really is about 0.24 if you check your calculator for 0.24. So I ran off the screen a little bit there. Okay, move that over. So 0.24 is the proximate slope of that secant line. 0.24. A little hard to write with a large stylus. These styluses are kind of old school on these smart podiums. So 0.24. All right, now find the equation of the secant line from 2 to 3. All right, so that's different. So basically, here's what's going on again. We've got this curve like that. Okay, and we just connected from x equals 2 to x equals 3. And that's this green line right here. And of course, it has a slope. We actually already calculated the slope. The slope of that secant line is about 0.24. Okay, and so now we'd like the equation of that line, right? So what we're going to do is go ahead and write y minus y1 equals m times x minus x1. And we're going to update it for this year. This is an old formula. You should have seen it many, many times. Okay, but we're going to update it for our purposes. Instead of x1 and y1, we're going to use f of x1 and x1. Okay, instead of y1, we're going to use f of x1. And instead of m this year, we're going to use a rock. Or sometimes we'll use something called I rock, which sounds like I'm bragging, but I'm not bragging. It's called I rock, instantaneous rate of change. Okay, so you can pick either point to be your x1 technically. So this is the point 2 comma square root of 2 plus 2. That's this blue point. Or you can use this red point 3 comma square root of 3 plus 2. It doesn't matter to me. Pick one. Do you want to use 2 comma root 4? Or do you want to use 2 comma root 5? 3 comma root 5, excuse me. I'm going to go ahead and use this first one, 2 comma root 4, because root 4 simplifies. Root 5 doesn't. So I'm going to use, instead of 3 comma root 5, I'm going to use 2 comma root 4, or 2, 2. Those are my x1 and my y1, or you could say my x1 and my f of x1. So I'm going to take these two values and put those in for my x1 and my y1. See? Alrighty, so we have y minus 2 equals, and then something times x minus 2. Sorry about my phone there. For a rock, we calculated that earlier. That's the slope of the green line, and that's our answer from part C, basically, so 0.24. So you can write this answer, or you can use, instead of the 2 and 2, you can use the 3 here and the root 5 here. Actually, it's the same answer in the end if you put them both into y equals mx plus b. Speaking of which, let's go ahead and do that. So I'm going to go ahead and keep the green there, not the red. I'm going to go ahead and distribute the 0.24 in. So now it's 0.48. and I'm going to move that 2 over. So it's y equals 0.24x plus 1.52. And this is traditionally how teachers want your answers written. Although I don't really care which answer choice you use. You can use this one or this one. They're both very nice. Okay, let's go to our next page. Let's talk about increasing and decreasing. So increasing and decreasing is a very simple idea. If a graph is a function like this, there are parts of the graph that appear to be rising and parts that appear to be falling. We call those increasing and decreasing in math, right? So let's just say that this is 1, 2, 3, 4. You can see that the curve is rising before you get to 2, and then it's falling after you get to 2, but not forever. It starts to actually rise again when you get to x equals 4. So now it's rising again, see? The red regions are called regions of increasing. The green region is called the region of decreasing. Now, if this graph stops here, and if this is sort of the end of the road, and everything kind of stops when you get to x equals 5, and there's nothing before x equals 0, then you could honestly declare the regions just using inequalities. So you could just basically say it's increasing, f is increasing over the intervals 0 to 2, and let's use inequality notation. So between 0 and 2, and it is decreasing over the interval 2. Let's use inequalities. I said we would use inequalities between 2 and 4. See. Now, I don't think you would say it's actually decreasing or increasing when you're at 2. So see where this star is? I wouldn't call that a point of increase or decrease. I would say that is a neither. It's neither. And same thing with at x equals 4. If you want to argue that it's rising at x equals 0 here, you could probably include that. It does look like it's kind of pointed, slanted up, you know. So, but I'm not going to stress endpoints too much. So if the graph starts at 0, why don't we just make it an open point? That way you won't even look there, okay? And same thing, let's look at the right side here. Let's make that a nice open point. That way you won't be wondering, should I include the end point or not include the end point? We'll just stick to this. Okay, now formally, what's going on that makes a graph look like it's rising is this. Oh, by the way, we always go from left to right when we judge if something's rising or falling. Okay, so sorry to those from countries where you read right to left. We go from left to right in math the same way we do in English reading. So do not treat the red as falling. You are treating the red as rising, and we're treating the green as falling. Okay, we go left to right always in math. Official formal notation, the reason that red region looks like it's climbing is this. For x1s that are less than x2s, f of x1s are less than f of x2s. This is called increasing behavior. F is increasing if for x1 is less than x2, f of x1 is less than x2. So here's what's going on. Here's what it means. You have 2 points, x1 and its y coordinate, f of x1. And you have another point, x2, and its y coordinate, f of x2. Okay? So we're saying that as long as x1 is the smaller number, so let's say this is 2 and this is 3. As long as x1 is the smaller number, the graph will look like it's rising if its y value is the smaller y value. So we're going from a small x and a small y to a larger x with a larger y. So the y for the second point is bigger than the y for the first point. So it's literally higher up. You have to rise and run to go from the first point to the second point. That's increasing behavior. And f is considered decreasing. Let's write that in green. F is considered decreasing if, and then we can rewrite this, if for x1 less than x2, f of x1 is greater than f of x2. This is just saying sort of the opposite. You've got this point, x1, f of x1. And you've got this other point over here, x2, but its y coordinate is less than that of f of x1. See? So you have these two y coordinates, but the second one is a lesser y value. And so the graph then appears like it's falling, see? Another way of saying it is you have to basically go down and to the right to go from the first point to the second point. And it's because the y is dropping. So we say that the y value is less for the second point. And we write that now this year, instead of y2, we write it as f of x2. Okay, let's go to the next page. Now, if your graph goes from increasing to decreasing or decreasing to increasing, you're going to get what we call a minimum or maximum point, actually in reverse order. So minimum, maximum. Okay, so I'll use a crayon for this. So this point here and this point here are a minimum and a maximum and a minimum respectively. Okay, so let's say that all of this is occurring, all of this is going on at x equals 1 and x equals 6. Okay, we would say that f of x has a relative max at x equals 1, and we would say that f of x has a relative min at x equals 6. Okay, another way to say that is the value of f of x at 1 is, and then maybe this, we know the y coordinate here, so maybe this is the point 1 comma 10. This is point 1, 10. You could say the value of f of x at 1 is 10, and it is a relative maximum. So you could actually say it that way if you want to include the y value in your explanation. Okay? Okay, and then the 6, you would say the f of, let's say that that's the point 6, 5. Okay, so this was a 10, and below it was a 5. So you would say the value of f of x at 6 is 5, and it is a relative min. Relative minimum. Okay? Okay, so maximum just means highest point in its region. Minimum means lowest point in its region. So just scrolling back up here real quick, there's a blank here that I left blank on purpose. The word that goes here is local. Local. Okay, and the reason we call this a local min or relative min is because when you are talking about the highest points on a graph, it is often the case where there is no truly highest point. For example, you might assume that this graph actually goes higher on the right, you know, it keeps going up, up, up forever, right? And if it does go up, 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 up forever, there really is no maximum point. Like, there's nothing highest. It's rising all the way up to infinity, you see? It's rising towards infinity. And the same thing for the minimum. You might have the graph falling deep down into the abyss. Why would we say that there's a minimum point? There's no minimum point, okay? But in this locale, in this region that I'm highlighting right now, in this region, maybe between x equals 0 and, you know, x equals 7 or something, maybe x equals 0 and x equals 7. In this region, we do have points that we might want to consider as highest or lowest, that sort of thing, okay? All right. So again, I'm going to treat the endpoints as open on this problem. So you're going to assume that this graph doesn't even continue. But we don't want to just say maximum, and we don't want to just say minimum, because there might be points outside what we're looking at that are higher or lower respectively. So we just pick a little window, look in that little region and say, oh yeah, there's the highest point, and oh yeah, there's the lowest point. Next is use a graphing utility to determine, or to graph f of x equals x cubed minus 3x plus 2 on the interval -2 to 2, and then determine where it is increasing or decreasing on that interval. Okay, so for that, I'm going to use a graphing calculator. And if you have your graphing calculator, get that out. If you don't, then you can just kind of follow along, but make sure you write down the keystrokes. When you turn on your graphing calculator, the screen's pretty much blank. You have to press y equals if you're going to graph anything. So you just type x to the third, that's x arrow 3. Here's your power key right here. Mr. Short's pit isn't working here. The power key is right here, pointing to it. There it goes, not circling. Sorry about that. X cubed, and then minus 3x and then plus 2, I think is what I have here. Yeah. And then because we don't want to look at the whole graph, we only want to look at a specific window. I said between -2 and +2. What I would like you to do is press window, and we're going to change the window. So we're not going to go from x equals -10 to x equals +10. We're going to go from x equals -2 to x equals +2 and graph it. Okay, this is the graph we've got. Okay, now it looks to me like, just kind of at first glance, it looks to me like this point right here is the relative max, and this point over here is the relative min. So maybe this is my rel max, and this is my rel min, right? I'll just put max and min for short, okay? Max and min. Okay, now if you had to ask me, I would say maybe that the relative max is at -1 and the relative min is at +1. That's kind of the x's that I think I'm looking at here. To really confirm that though, you need to use the calculator's internal calculation possibilities. So press second in calc, and let me clear this screen. Press second in calc, and then go down here to maximum. It's option 4. Okay. You're going to go over here to the left side of the point you think is the highest. So let's go over here, click, 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 press enter. And you're going to go to the right of the point that you think is highest. Oops, not sure how it jumped. Sorry, kind of jumped across the screen at me there. And then press enter again. And now you can see that it gave you these 2 little arrows there. See it? That means that the calculator is going to search between here and here, which is where you clicked, to find the highest point. Okay, so now go ahead and press enter one more time, and the calculator should do its thing. Okay, according to the calculator, the maximum happens at x equals -0.999973, y equals 4. In other words, that's -1, 4. Okay, so it looks to me like the relative max is at x equals -1. Okay, that was my original thought. Now, the relative max value of the function is 4. So if they ask you where is it at, you give the x. So at gives you give the x. If you see that word, use x. If they say the relative max is, if they use the word is, then you use the y coordinate. So -1 is for where it is at, and 4 is what it is. So the answers to this are -1 and 4. Okay, make sure you know that. Okay, let's go over and look at our relative minimum, which is on the other side of the graph here. I'm thinking it's at x equals 1. Let's see if we're right. So we don't have to guess. We're going to go second calc and go to minimum. Then we're going to scroll over here. Well, that thing keeps jumping off the screen. I don't know what's going on. Sorry about that. Let's scroll again. Scroll, 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 scroll. I'm going to try to go to the left side of that point that I believe is the minimum. Since I believe the minimum is right over here, I'm going to get my cursor just to the left of that and press enter. Okay, now I'm going to go over here, scrolling to the right, scrolling to the right. To the right of the point I believe is the minimum, and I'm going to press enter again. Okay, so the calculator again gave me these 2 little arrows. It just means it's going to search in this little window for the lowest point. I hope it finds my red one. I think it will. So let's see if it does. Let's press enter one more time, and it's at 1.0000009, and then it says 2.4 times 10 to the minus 12. So this is pretty much x equals 1, you got to admit. And this is pretty much y equals 0. I mean, 2.4 divided by a trillion, that's basically 0. So the calculator sometimes has a little trouble just writing the number 0. So on this one, the relative max is at 1. The relative min, Mr. Schler made a typo. This should say the relative minimum. Sorry about that. Oops. The relative minimum is at 1. The relative min value is, and then here we lift the y coordinate, 0, 0. Okay, sorry about that. Too many copies and pastes. Okay, next. What's the difference between an odd function and an even function? Okay, this is a very, very important concept that I will drill you on all year long. So basically an odd function is a function where f of negative x is equal to negative f of x, okay? And if in a graph of something like that, it doesn't have to pass through the origin, but it does have to have what we call origin symmetry. So this is an example of an odd function, okay? And basically, an odd function has this origin symmetry. It just means that here's the origin, right? If you pick a point over here at, let's say x equals 1, y equals -1, if you take those two and you just switch the signs, you make the 1 negative and you make the -1 positive, that's going to give you a new point, right? So if you just change the signs on these guys, it's going to become -1 +1. That point also is on the graph. See that? Interesting. So I'll show you another example. Let's say that here's your graph. That wasn't a very good drawing, but this is your graph. And you're over here at 2, 0. If you negate or change the signs of these two coordinates, right, 2 and 0, you get, if you change the sign of the 2, you get -2. If you change the sign of the 0, you get just 0, of course. That point is actually on the graph also. It's also touching the curve. Interesting. Okay. Here's another one. I'm just trying to make sure you get this. So I'm going to draw that same picture again. This time I'm going to pick the point 3, 2. So this is the point 3, 2, this red one. If you change the coordinates of that point to opposite and opposite, like keep the 3 and the 2, but just change them to both negatives. So now it's -3 and -2. This creates a new point, but guess what? It's on the graph. It's actually over here, right on the graph also, -3, -2. So this is what we call a symmetry. It's when you can either fold or rotate a shape and it looks the same either way. What's interesting about this is if you take that graph that I drew, right, and you want to see that odd symmetry, that origin symmetry, the easiest way to do it is to go ahead and take it and just spin it upside down like this. When you spin it 180 degrees and it looks the same as it used to, that's pretty much visual proof that your graph has origin symmetry. Okay? That's called odd symmetry or odd function, and they have origin symmetry. Okay? All right. So in general, if there's a point over here at x, f of x, there should be a partner point over here at -x, -f of x. I'm sorry, I didn't mean to say that. I meant to say there should be a point over here at struggling with my pen here. There should be a point over here at -x, comma, -f of x. Like that. Okay? All right. Now, let's give an actual example of one of these. Let's say I gave you f of x equals 2x cubed plus 3x. You can show that this is an odd function by doing the following. The first thing you do is change the x's to negatives, and then you multiply the whole thing by -1. Okay? So first you change the x to a negative. So you go like this. This is called f of -x. You just insert for each x a -x. So I just changed 2x cubed to 2 times -x cubed, and I just changed 3x to 3 times -x. So I just inserted negatives on all my x's. And then that sort of takes care of changing the x coordinate. Now I'm going to change the y coordinate, and I do that by multiplying the whole function by -1. Okay? So I've got the red minus signs, and I've got the blue minus sign. Okay? The reds are inserted on the x's. The blue is inserted outside the function. The red ones change the sign of x. The blue one changes the sign of f of x. In other words, it changes the sign of y. Okay. F of x just means y. Okay, so I'm trying to see something here. If I simplify, of course, inside first, I get 2 times negative x times negative x times negative x. In other words, negative 2x cubed. And I get 3 times negative x. In other words, minus 3x. And then this sign outside, this blue minus sign, changes the signs of what's inside. So I distribute that negative now, and I get 2x cubed plus 3x. So what happened was I changed the signs on both x and f of x, and it turned out to be the same function I started with, okay? So I started with 2x cubed plus 3x. I ended with 2x cubed plus 3x. What does that mean? That means when I change the signs of both x and y, I end up with the exact same graph I had before. Okay, that's what that means. And this proves that it's an odd function. And this is the only way to convince me that the function is odd. You cannot do this. Graph it on the screen and say, hey, Mr. Shore, you know, this thing, I think it looks the same right side up and upside down. Like, I can rotate it and it looks the same. That's convincing visually, but that's not proof. The proof is right here in this work. Okay? Now let's talk about even functions real quick. An even function is different. Trying to keep my time reasonable here. An even function does not have, as the odd function has, origin symmetry. It basically has what we call y-axis symmetry. So this is actually a little bit easier. Okay, a graph like this one is considered an even function. In fact, you might remember this graph from Algebra 2. This is just the graph of y equals x squared, which has an even power of y equals x squared. Okay, and so this is an example of a graph of an even function. But the definition of an even function is f of negative x is equal to f of x. Okay, I say I don't understand what that means. It means this. If you look at a graph of an even function, you always find the following properties. If there's a point at 1, 1, let's say, then there's going to be a partner point for it at negative 1, 1. Let me draw another example. If there's a point at 2, 4, there is a partner point over at negative 2, 4. If there's a point over here at 3, 9, there's a partner for it over here at negative 3, 9. In other words, if you change the x of a point, say 3, 9, just the x, you just change the sign of the x, the graph will contain that point as well. So basically, we're only changing x. And these graphs are all even functions. I'm drawing several now. This one, this black one, this purple one. That wasn't a very good drawing. Let me redraw that. This purple one. These are very easy to spot because the y-axis cuts them right down the middle. See that? Cuts it right down the middle. And so for any point that's on the right, let's say it's the point a x comma f of x, there should be a partner point on the other side at negative x comma f of x. They have the same y value, but the x has been switched to a negative x. So an example of this would be if I gave you, let's say, f of x equals 2x squared plus absolute value x plus 5. Okay, this graph, without graphing it, I can tell you that it looks like one of these graphs above. How do I know that? Well, because if I take my x's and I change them all to negatives, so I'm changing the 2x squared to 2 times negative x squared, changing the absolute value of x to absolute value negative x, changing the 5, well, there's no x there, so just leave the 5. This means 2 times negative x, also known as 2x squared. The absolute value of negative x is asking how far is negative x from the origin is what it really means. Well, it's the same distance x is from the origin. So I could just simply change absolute value negative x to absolute value x. No penalty there. And then there's a plus 5 here. So notice that what I have here is the same thing I started with back at the beginning. So there's no difference between f of x and f of negative x. There's no difference. Okay? And this proves to me that this graph is an even function. Okay? So just in way of summary, an odd function has this property. F of negative x equals negative f of x. Or you could write it this way. Negative f of negative x returns f of x. And an even function has this property. F of negative x is exactly the same as f of x. The first ones have what we call origin symmetry. Okay. The second ones have what we call y-axis symmetry. But we don't trust graphs to tell us if something's odd or even. We trust the functions and the examples that I showed you.